All right, and welcome back to Mechanical Systems Design. In this video, we will launch Project 3. So up to this point in the course, we've mostly been drawing on our prior knowledge of statics and strength of materials to design mass-efficient components. For this next part of the class, for the next 6 weeks, we're going to bring in some new tools to make things even more exciting. And that includes motors, gearboxes, assemblies, some other things. And in this next project, we'll really be focusing on electric motors and gearboxes. We're calling this project Mission Improbable, and it's an individual project in which you will characterize a motor and gearbox, choose an operating point and gear ratio, fabricate a capstan with your desired properties using a starter design we'll provide, and then test the resulting system performance, upload your data and video, and then explain your design in a brief written report. And where we're doing this is to really learn how electric motors and gears work. The best way to deeply understand something is to try to synthesize and apply that knowledge. And this is a good opportunity to do that. Another objective here is to learn how to select a motor operating point and gear configuration for a particular task. And that's something that will come up a lot if you go out into the world and design products. And finally, we'd like to think more about how we design experiments to characterize components or systems that we've developed. That's a super important skill to have in a wide variety of potential careers. So before we get started, this is a great time. You're going to spend some time digging into this technical content, but really quickly, some practical things to think about are whether you have the materials you need. So check that you have your Tamiya kit, should look like this, and access to a video camera, ideally one that has a slow-mo setting. And you might be tempted to put your hands on this thing right away, start building it, but before you do, I strongly recommend you read this whole project description, the Tamiya kit, assembly instructions, and some extra tips that we give you for putting it together, and the motors and gears topic readings, because there's a ton of helpful information in there that's going to help you avoid some common missteps. So our task here is, what we're going to use the motor for is we'll connect it to this gearbox and capstan to form a winch that is intended to lift a set load as quickly as possible. And you can see some of the specifications here. The way we're setting this up is to have some table or other rigid surface that's high up off the ground, where your motor and gearbox will be set with the capstan hanging off the edge and a string wrapped around the capstan that connects to a load. And then you'll lift the load. First, it'll come off the ground, and then it'll pass some mark, and then a second mark that's 1 meter away. And the time it takes for the payload to traverse that 1 meter gap is the thing that we're trying to minimize. And this project is inspired, the name at least, is inspired by the 1996 movie Mission Impossible. Here, this team of spies is trying to break into this secure facility, which they don't have video cameras for some reason. Anyways, Tom Cruise here is dangling, and we need to replace this person with a powerful motor that can lift him up so he can complete his mission. All right. So what is this motor that we're using? Well, as part of that planetary gearbox kit, you'll receive a Mabuchi motor. And there's a manufacturer specification sheet provided online. Unfortunately, the specifications are not very accurate, most of them. So we're going to need to conduct our own experiments to identify the key characteristics of the motor. And those include the coil resistance and the motor constant and the motor friction due to brushes. And we'll learn about what those things mean in the upcoming topic readings and videos. And we'll discuss strategies for designing experiments to identify them robustly in our coaching sessions. We have previously identified some other characteristics that are a little trickier to get at, including the thermal properties of the motor and the maximum voltage that can safely be applied, which we're setting at 6 volts for this project. Now, a quick warning before you start plugging in your motor: it can overheat easily. So if you, we're going to learn all about motors and that sort of thing, but one thing to know is that if you stall the motor, you prevent it from spinning, then the current is maximized, and that current heats up the coil. And when it hits a certain temperature, the insulation burns, and then it shorts and the motor doesn't work anymore. So for example, with this motor, if you stall it for just 10 or 20 seconds at that 6 volts, it will overheat, and then it won't work for you anymore. And it takes a long time to cool down, actually. Surprisingly long time, about an hour, to get back to close to room temperature after it's been close to its maximum point. And here's a quick a video of this happening in real life. You can see all of a sudden the motor slows down, the current spikes, and the magic smoke here comes out of the motor. And once that magic smoke gets out, you try to catch it and push it back in, but it's gone, and the magic just doesn't work anymore. So we've also provided you with a power supply, and there's some good tips in here about how to use it effectively, both to power your motor and to measure the current that goes through your motor. We provided you with this gear kit that you can reconfigure to get different gear ratios. One thing that's a really important property of gears is their efficiency. And the manufacturer doesn't provide a good estimate of the efficiency here, so we'll have to perform our own experiments to characterize it. That's something we'll learn a little bit more about from topic readings and videos, and we'll discuss in our coaching sessions. Now, before you start playing with this stuff, another quick warning: the gears can hurt you too. So this little system can actually produce a lot of torque and power, and the output can dremel or tear your skin and all that kind of stuff. So don't grab it with your bare hands. If you need to stall the motor, the way to do that is to choose a low gear ratio, put on your capstan, and then hold the capstan and motor firmly in place before you turn it on. And remember, only to stall it for a second or two at a time. We're providing you with some starter CAD that you can find on Canvas that you can modify to meet your desired radius and wrap width. And you may have to do some little tweaks to the CAD to get it to compile right, but the main feature that you'll want to preserve is that interface with the output shaft of the gearbox. As I mentioned, you'll want some thin string and a payload. Don't flop that around and hurt yourself. And then we have some tips here for how you can, some of the practical tools that you could employ in the experiments that you design to characterize your system. The way we'll evaluate your project is first, we'll look at the accuracy of your characterization and calculations. So we'll have you estimate that coil resistance, motor constant, motor friction, and the efficiency of a single stage of your gearbox, and report those values. And if you get those pretty close to accurate values, you'll get full credit. If they're a bit further off, about half credit, and if they're kind of wildly off, then no credit. And we'll also ask you to estimate the electrical power consumption of your motor during the final test that you provide us, and the overall system efficiency, electricity to potential energy, and the efficiency of the motor and the efficiency of the transmission. And if these are calculated accurately based on the information you provide us, full credit; a little bit of an error, half credit; and a lot wrong, no credit. And that will be 20% of your project grade. We'll also have a performance-based grading element as we had in projects 1 or 2. In this case, we'll base it on the time to lift the payload for your final configuration. And there are some design challenges if you're feeling excited about it. Obviously, fastest lift. Now, we will probably round the times, and so it's possible that lots of people will achieve a really fast lift time, and we may give up a lot of awards for this project. The second one is the most robust approach to characterizing the motor and gearbox properties. So how can you be most certain that you've got a good estimate of those values? And thirdly, the most convincing summary page for your report. And what is that report going to be? Well, once again, we'll have a 3-page summary report. The first page will include a photograph showing your system in its final configuration and your test setup, and then a 300-word summary of your process for estimating the motor and gearbox characteristics, and why you used this process, how you chose the applied voltage, gear ratio, and capstan radius, and why those values are effective. And finally, how you calculated the powers and efficiencies from your system. And once again, we have a high bar for the writing here. We expect it to be really clear and convincing, to draw on the kinds of concepts that we'll be discussing over the next 2 weeks. And we expect you to write it and edit it until it's of high quality. On that summary page, you'll also list your estimates, your choices, and your calculations for power and efficiency. And the next 2 pages will be on the motor and gearbox characterization and the power and efficiency calculations, where you'll give us the equations you used and explain what data you input into them. So the overall grade will be 20% on your calculation accuracy, 10% on that lift time performance, and 70% on your reporting. So I know this is very new stuff. It can be a little daunting at first, but once you get into it, you're going to find it's really exciting. And as you gain these tools, you'll be able to design all sorts of pretty awesome new products. So have fun with the project. We're really looking forward to working on it with you.